Hello everyone, my name is Nathaniel Lee, and today I'll be presenting the short paper titled Metal Price Spike Prediction via a Neuro Symbolic Ensemble Approach. So, initially when we were looking into this domain of time series price data for various commodities, what we found is that a lot of the existing work is largely regression based and they use predictions by a single model. And regression certainly has its use cases. It's useful for predicting trends and such in a time series. But when we took a closer look at a lot of these works, we found that while they reported very good metrics, the trends produced by their model weren't very good at capturing these spikes, these points where a large shift, whether it be up or down, happens within a very short amount of time. So that's where we thought it'd be interesting to view this problem from a risk management standpoint, right? Where we try to classify where spikes would occur in a time series, because we think this could be helpful for mitigating economic risks. So next, let's look at a quick example of how classification in a time series would work before seeing how our idea kind of evolved from there. So here we have a CNN, and let's say it predicts 3 spikes here correctly. Okay. And then next we have an LSTM. It predicts the same spike that a CNN did there, but it missed out on the 2 other spikes that a CNN did catch. However, the LSTM was also able to catch another spike here that a CNN couldn't. So even though the LSTM performed worse overall than the CNN, we had an idea, right? So what happens if we try to learn rules from various model predictions, even from models that perform worse overall? Because what happens if we can use these rules to improve a base model's results? And yeah, that's kind of how we turn this into a Neuro Symbolic problem. And for that, we actually have a framework called EDCR to support us that was developed by our lab member. And I'll be spending this next section talking about this framework for quite a bit. But first, let's just dial it back and look at the core principle that kind of guided the design of EDCR. And that is metacognition. So metacognition can be defined as the understanding and awareness of one's own thought process. So here's a quick example. After arriving in Abu Dhabi, you think you see a buddy, Jimmy, in the airport. And you're about to run up to him, you're about to greet him. But wait, you just remembered. Jimmy should be in America right now because he told you that he was going to be in a conference there. So, there's no way he'd be here. So using that, you can deduce that that person is not Jimmy. So this entire process of reasoning with some knowledge that you have or some thought process, that is metacognition, right? And in our daily lives, we're constantly doing this to kind of correct ourselves in tiny little ways. And that's what EDCR basically is. It's a metacognitive framework that learns from what we call detection rules to identify misclassified labels, and learns from what we call as correction rules to reassign those misclassified labels to new ones. So let's first take a look at detection rules. So how detection rule works is that we first have a condition set DC that can tell us when a model prediction is incorrect. And let's say we have any condition within that condition set to be true, and we have a base model that predicts class I for a certain sample omega. We can then assume that that prediction from that base model for class I is incorrect. And what we would do is we would temporarily flag it to an unknown class or just erase the label and pass it to the correction rule. And how the correction rule works is that if we have any condition class pair in the larger set to be true, what we do is we then reassign the previously erased label to that new class. So yeah, here's the flow of how EDCR works. You first have a model that produces its own set of predictions. Then you would have a set of conditions, and these conditions can come from domain knowledge or it can come from model outputs, model predictions. And using those conditions, you would then learn error detection and correction rules. And you'd find where the base model's predictions had mistakes in it, and you would try to reassign them to new classes instead. And from there, you would get some improved performance. However, it's worth noting that the original EDCR framework was designed around a multi-class classification problem. So that's why in the detection rule, it made sense to first erase the label because you can assign it to like a variety of other labels instead. But in our case, we were dealing with a binary classification problem because we were only trying to predict non-spikes or spikes. So in our case, it didn't really make sense to have the label erased in the detection rule, because if we have a condition that can tell us when a model's prediction is incorrect, and in particular, in our case, we're only interested in flipping potentially incorrect non-spikes to spike classes, because spike classes are the minority class and they're also the class of interest. So yeah, it didn't really make sense to erase those labels, because why not just assign something we called incorrect non-spike, and why not just flip it to a spike class instead? So here's a clear example. Let's say we have a base model and it identifies a sample omega as a non-spike. And then in our case, since we're using an ensemble model ensemble as our condition set, so they all have their own set of predictions and we're using those as conditions. And let's say one of the models in the ensemble, CNN of variety 1, CNN variant 1, predicts that sample to be a spike. So in that case, we use this as a condition, and since base model predicted a non-spike, we can then assume that that is incorrect, and we would then just flip it to a spike. No need to erase it, we just flip it. So yeah, that's how we kind of adapted EDCR to our problem, where the idea is that we didn't really need to distinguish between detection rules and correction rules anymore, because in our detection rules itself, it was performing corrective actions. And also we added a top F1 filtering method to this algorithm, because the idea is that since we're using model predictions from the ensemble as our conditions, we can first prune the condition set by only taking the models with the best training F1 score and then adding them to the condition set. And in our case, again, since we're only flipping potentially incorrect non-spikes to spike classes, it was impossible for our recall to drop after applying our algorithm. Like, our recall would only either stay the same or it would increase. But the danger of having it increase, which means adding in more spikes to the prediction, is that what happens if we incorrectly change something that should have remained as a non-spike, and what if we change that to a spike instead? So in that case, the prediction would drop. So yeah, that's why our goal with our experiment was to see if this algorithm could maintain the precision or at least improve it while increasing recall. Or in the worst case scenario, at least try to keep the precision recall trade-off at a minimum or more to our favor. But yeah, first let's look at the setup, then we'll go into the results later. So the commodity that we chose to perform these experiments on were metals. What we use is cobalt, copper, magnesium, and nickel, sourced from the years 2020 to 2023 from the website investing.com. And then after we got the time series, we defined spikes as values that exceed or fall below the rolling mean by 2 rolling standard deviations with a window size of 20 days. Though it's worth noting that this is not the only spike definition that could have worked, it's just the one that we decided to go with for this experiment. And as for the models that we used for our experiments, what we used was 4 main architectures. We had RNNs, LSTMs, CNNs, and CNN with attention, which we'll just call as attention models from here. And for the architectures, we then generated 4 variants of RNN and LSTM, and 12 variants of CNN and attention. And how we created these variants were by tuning a couple of hyperparameters like filters, kernels, and layers across the board. And here is how we kind of use those together in our experiment. So here's our flow. We first have one of the model variants produce its own set of predictions, and we would use that as like the base model. Then we would then form a model ensemble which excludes that base model, and this ensemble would then produce its own set of predictions, which we'll use as conditions after applying the top F1 filtering, which I mentioned earlier. And now that we have this pruned condition set, we can then learn rules to modify the predictions. And let's see how that turned out. So this was the most significant of our findings. We found that in 3 out of the 4 metals tested, when we applied EDCR to the best model in terms of F1 score, we managed to get a pretty nice bump of over 10% in F1 over the original score. And as for more detailed spread of data, we decided to do an analysis across the four metals, where we look at the best performing base models in terms of precision, recall, and F1. And we were interested to see how EDCR would apply to these base models. And so these are the base models, and how the naming scheme works here is just like something like a CNN1 here would just have a different hyperparameter compared to CNN2 here. But yeah, these are the base model results, and after applying EDCR, we got the new set of results. And what we found is that in most cases, we actually managed to achieve our goal of improving recall and precision at the same time, which is nice. That means we're just adding in strictly correct spikes back into the base model's predictions. But what we found is also there were a few cases where EDCR did not work, it did not apply, and we found that this generally happens in cases where there is a large class imbalance because there's not a lot of false positives, and false positives is kind of required in one of the filtering conditions that we use in forming the condition set for our detection rules. And there was also one case where we found a precision and recall trade-off, actually. And we still found this to be in our favor, actually, because for a small drop of precision, we actually managed to get a really nice bump in terms of recall and F1. And like even across all the metals, across all the best models we got here, this EDCR applied model actually has the best F1 score. So yeah, in that case, we found it to be still pretty nice in the end. But yeah, to wrap up, what we did with this work is we adapted a metacognitive framework to ensemble multiple neural models to predict spikes. And generally, the results were pretty favorable. And as for future work, we think it'd be interesting to extend it to other metals or other commodities for more robustness. And we also think it'd be interesting to incorporate probabilistic semantics into the EDCR framework, just to add more nuance as to when we utilize these rules. And lastly, I think it'd be interesting if we could adapt EDCR to be used in a time series regression-based problem. Because as mentioned at the start, most of the previous work done in this domain is regression-based, so a lot of the state-of-the-art models were also designed around regression-based tasks. So it'd be interesting to see if we could get a way to get EDCR to improve upon those state-of-the-art models' results. But yeah, that's about it. If you want to learn more about our paper, you can scan the QR code to the left. But if you want to learn more about the original paper that introduced EDCR, you can scan the QR code to the right, because there's a lot more technical details there if you want to see how you can apply it to your specific problem. But yeah, thank you for listening.